Okay, here's a start. And then, so today we're going to talk about chapter number 12 in the R4DS, R for Data Science book. Stefan is going to lead us in our conversation. And so, Stefan, I'm just going to turn it over to you.
Okay, awesome. Thank you. Let me just share my screen. Is this working? Can you see my screen? All good? Okay, perfect. Okay, so today we're talking about logical vectors, and our learning objectives are to understand what logical vectors are and in what situations we are using them. Then how do we generate logical vectors? We are also going to look at how we can then use those logical vectors to filter data. This is actually something that automatically happens under the hood when we do the filter function in dplyr. And how we can use logical vectors to create new variables and also to create summaries. That's one of the neat things I learned before. When I saw that, it was like, oh yeah, this is totally awesome to use logical vectors for. And we're also gonna talk a little bit about Boolean operators, so and, or, and not. And I think we've encountered those already in the filter section of the tidyverse. And then we will also try to understand how missing values are going to affect that. And that can be sometimes, you have to kind of stop and think about it, what missing vectors actually mean. Okay, so a logic vector has two possible values, true or false, or also 1 and 0s, basically. And so they're very important when we filter our data or process them in any other way. And so the possibilities, like I just said, true and false. And then there's also the possibility of missing values. And the most important part about missing values is how you deal with them and how you act on them and how Booleans act on them. Yeah, so here it's exactly that. So NA values can be tricky because some of the operations are kind of unexpected if you don't know what NA exactly means. And I thought this, I think we're going to talk about this later, but there was a really nice section actually in the chapter that I think made it really clear what an NA value is and why. One of the most confusing thing is why NA equals NA isn't true. Let's just put this here. I think, and the chapter I thought made that very clear, but maybe we can talk about it later. Operations, okay, and then so we have different operations we can do. So either we can do comparisons, and we've seen that already with the filter function to generate an actual logical vector. Then we can use Boolean algebra, so that's and, or, and not, and also exclusive or, and we encounter them in a minute too. And then we can do conditional transformations. So that is like if else, and then also case when, which are very neat. And especially encountering case when, if anyone ever went down the rabbit hole of having a lot of nested if else's, and it gets really confusing. And then you learn about case when, or like in other programming contexts, it's often like switch or something similar. It's like, oh, it makes it so much easier to read code. So that's really, really easy. Better to think about the logic of a function in that way. Then one of the things to do with logical vectors is actually use them for subsetting, which is a base R function. So those are the brackets that we encounter in base R, and I thought the chapter also provided some nice examples why you would subset even within mutate function, for example, because it makes sometimes the logic a little bit easier, like you can follow a little bit better. But it can be also daunting. I find it so verbose, and one of the nice things about the tidyverse is that it gets rid of all the verbosity from subsetting. And then also, how can you summarize logical vectors? And those are the examples, I think, was mean and sum to summarize logical vectors. And we're going to look at that. Okay, so how can we generate logical vectors? So either we can do this by comparisons. And so these are either equal, which are two equal signs, or not, which is exclamation mark and equal sign. The less than, less equal, larger than, and larger than equal. So we encountered all these. And then one to many is like the in function. And just as a reminder, there was also this cool example that someone brought that you can define your own not in function quite easily. I would have to look that up, but it was in one of the earlier chapters. I forgot. And I was like, I took a note. It was like, oh yeah, this makes total sense. So one-to-many comparisons is very convenient often. And so, yeah, it says here that comparison is often when you do when logical vectors arise, and often like when you try to get an idea, like in your data exploration, that's very common. You want to know, you know, all the penguins that have are larger than a certain size or whatever, then you can use those logical operators and subset your data that way. Okay, cool. Yeah, and so unless the logical vector is already provided, the observed variable is Boolean. Okay, yeah, that makes sense. Cool. So here, generating a logical vector, you use the mutate function, for, and then because that's the function you use to generate new variables, just as a reminder. And so in this example, we determine when it's daytime by looking if the departure time is larger than 6 in the morning. And just as a reminder, so keep the use that only keeps the variables that you used in this mutate function and any variables that have been newly generated. That's very convenient when you do like exploratory stuff and want to see if your operations are actually doing what you expect them to do, instead of having all the extraneous columns, because otherwise, you know, you get your little printout in your console and there's so many other stuff. So keep is a nice way to get a kind of a nice idea if the steps are working the way you're expected to. So that was also, it's always nice to see the stuff I had forgotten, and it was like, oh yeah, I should use more keep, because otherwise I usually like type it into view so I can see it in RStudio and then see the whole thing, but then I scroll because, you know, the newly generated columns are at the end. I find it really convenient to use the keep option here, parameter. Okay. And here it then shows that you can use a logical vector for filtering. So it only keeps the rows that have a true in the logical vector. And so that's just how you then keep all the rows where it's daytime. And I don't know, I don't remember. Basically, when you do filter and do daytime departure time larger than 600, then basically those two steps are just happening in one, instead of having two separate steps. So that makes it just easier and your code easier to understand.
Just a step back, because this was interesting to me. Yeah, just if I could just jump in real quick, go back to the previous example. Like, it's just interesting to me because like when you use the mutate here, you're creating the logical vector for a new column, and then you're adding that, or you're using that column in filter. You know, I'm used to, and I know this is like just an example to show like what's happening on the back end when you filter, but it's just so weird to me that like when you think about filter, it's just creating logical vectors on the back end and filtering based on that. And so you could just put a logical vector in there to only return true. So yeah. It's more of a comment than a question, but it was just interesting to see that, because it's just interesting to see how filter actually works. Because when I think of filter, I always think of like the statements or the conditional logic that I put in to the filter statement, right? And so the one thing that I always get caught up with is like when I'm trying to filter by like a string pattern or something. I know we're not talking about strings, but like that always confuses me, where you go like filter column name equals stir detect something, and at the base of it, it's like it's just creating a logical vector, and then it's using that logical vector to actually filter it out. And so I don't know, that's more of a comment than anything, but it's just weird to see just like the single statement or the single column being referenced in filter, and then it actually filters it out. But I don't know.
Yeah. No, it's good to know. And I assume if you would go exploring into the functions, that's exactly what it would create, right? It would create the logical vector and then use that to subset your data. That's what I assume. But I haven't looked at the filter function. But it's good to know what things are happening under the hood. Okay. Is that all you wanted to add, Colin? Yeah. Okay, cool. So, and then here's an example where we use in as a function. So instead of having just a comparison between to one possible value, you basically have three different ones. So just as a reminder, 1:12 just means it generates a vector which has 1, 2, 3 up to 12. And then each one of these values is compared if it's contained in this other vector, which contains 1, 5, and 11. And then you see here the first value is true because 1 is contained in this vector with 1, 5, and 11. And then if you count 1, 2, 3, 4, 5, then the fifth value, which is 5, is also true because there's a 5, and so on. So that's just an easy way to compare and have a comparison with multiple values at once. Okay, and I'm not going to jump the gun because the in operator is also very interesting when you want to compare to NA. That's also one of the things I took away from this chapter, but I think it's going to come up, so it's really good. Okay, so here it just shows that the comparison actually is a logical value. So if you use the function class, it gives you what kind of data type you have, and so it shows you you do the comparison here for the departure time to 600, and then you get as a class logical. And I'm not sure why we're doing length and head here. I think it's just showing some other information. Yeah, so this is a comparison generates a logical operator for you. And that's important later when you do subsetting in base R. That's how you get your logical vector to actually subset your data. Okay. And so here it makes exactly the point we already discussed. So you do not need to store the logical vector if you don't do anything else with it. You can just have the comparison as part of your filter function to subset your data to those values that are larger than 600 in this example. So it just makes it more succinct instead of generating vectors that you might not need for anything else. Okay. So we can generate a logical vector by either doing the comparison, and now it talks about combining logical vectors. So, and the most typical logical operators people use is AND, which is the ampersand, or which is the in Linux command line, it would be the pipe. I don't know what else, like vertical line. Then not is exclamation point, and XOR is exclusive OR. Also something that I thought was really nice because it was pointed out in the book. So exclusive OR, the difference between OR and exclusive OR. So if you have two Boolean values, I think that's coming anyway. So maybe I'll talk about this later. And then, so then there's functions that do exactly the same. So if you don't want to use those operators, there's an AND function, an OR function, a NOT function, and the Magager, I don't know how to pronounce this, package, which was usually where the pipe, the old pipe came from. So that's maybe why people know that package. But I would say I don't encounter that much. I usually only see ampersand and the other symbols for operators. And then he says in numerical operations, so if you would like add, for example, a false to a true, you would get, a false would be a 0 and a true would be a 1. So if you add a false to a true, you would get a 1 because the false would resolve to a 0 and the true would resolve to a 1, and 0 plus 1 is 1. And so because of that, you can actually mimic the AND operation by the p-min function. And I don't know what the difference between min function and p-min function is, as I didn't look it up. But the interesting thing is that min would get you the minimal value, right? So and the AND operator gives you only a 1, maybe this comes later. So and gives you a 1 if both of the values are true. So true and true gives you true, gives you a 1, and everything else gives you a false. And so the pmin function basically would look in your vector, and if any of your values is a 0, then it would return you a 0. And that's basically what the ampersand does for you. And the reverse is true for or. So if you have if any of your two values are true, then it will return you true. And the pmax function does exactly the same thing. So if you have a 0 and a 1, then it would return you the 1. And that's why it kind of acts similar to the OR function. Does that make sense? I thought it was just neat to see, and then it makes you wonder when you read this example, because I don't think that was in the book. I was like, oh, is that how it's implemented? I was just curious, like how the function actually works. Okay,
Yeah, there's a it's the package is Magritter, I think is how they pronounce it. Magritter.
Magritter, thank you.
Yeah, Magritter would be yeah, that's where the pipe comes from. But some interesting stuff that you mentioned here, because I was curious, and this goes back to like some of the previous stuff about like, false being 0, true being 1. Like I was looking at, because we had class. If you do class of true, it's logical. But then I was wondering what type it was, and then I just typed it in. Type of true is logical. It's not numeric, which is interesting to me, And I was just like, so it gets its own type. It's like a true is actually type, even though it can be represented as a 0 and 1. Which I just checked it right now, because I was like, oh, it's probably a numeric on the back end, but it's not. It's its own type. So it's just interesting to me that that's the case. But
yeah, and I think that might be, isn't that different to Python? It's been so long that I use Python. I thought if you have a numeric vector that has only 0 and 1s, it treats it as a logical. While in R, you actually have to coerce it into a numeric vector, I think. But I might be wrong.
That's
Anyway.
interesting. I don't know. DJ's my Python guy. Did you know DJ? I don't know. That's interesting to me. I don't know. But the other thing too, that's the other quirk that I say while we're on this topic of true and false, 0 and 1s. One quirkiness of R is that you can use capital T and capital F. Although I say that most general convention that I've seen, people say avoid using capital T, capital F. But you might come across some older code where people use capital T and capital F, and it is the same representation. It is the same type. It is a true and false logical. So
is there a good reason for that, or is that just, does that come from the tidyverse style? I was just curious. I also do always spell it out, but I was like wondering if there's a good reason to not do it.
That's a great question. Like, I don't know. I think it comes from like base. Like, I think it was just to deal with like I don't know the actual reason behind it of why T and F is defined as it, but what I would assume is a lot of the base design was to try and get rid of that verbosity, to be like really succinct. And so you'll see like there are some like conveniences built into R that it will that you don't have to spell things out, like partial argument matching.
Oh,
right?
yeah,
You
yeah.
only have to, So I assume that would be partly the case to make it convenient, so you don't have to write out true and false. But like, it's kind of interesting to see how people are like, no. Even though you have this convenience, write it out. So it's one of those weird, quirky things about R that some people kind of like don't like. But yeah, I don't know. That's just the way I view it. Is just like it's just a convenience that goes against like general convention. Sorry, go ahead.
No, I no, totally. I was curious because I thought it was really interesting. Like, what is it called? Snake case, like that you have underscores for space and names. The justification for it, instead of like having periods, is that periods usually indicate methods, so some function that belongs to a class, an object. And to basically be more explicit, no, this is just space. And that made sense to me. Okay, then because you encounter this so often, periods in other programming languages, so it seems kind of cleaner to use underscores for spaces. So it made a lot of sense to me in the tidyverse style guide. Anyway, okay, cool. Sorry for this aside. Let's go to the next one. Here are all, so these are Venn diagrams, which show you what these different operations give you. I don't think I need to go through it, but is there anyone who has issues with Venn diagrams? I assume most people have encountered them. I mean, you get used to them as soon as you start learning about Boolean logic, right? So those are all the different options. I think one of the things that I meant to mention earlier, what I liked about the chapter pointing out that in natural language, in our language, when we say or, we mean usually either one or the other, which is exclusive or in Boolean logic. And I think that's kind of good to keep in mind when you think about writing down your logic, what you actually mean, because often, you know, when you write your code, you might first describe what you're gonna do. And so that's good to keep in mind. I thought that was a neat trick. Okay, and here we're generating a logical vector. And in this case, we have two comparisons. So both of these comparisons would generate as a logical vector, and then the Boolean operation does the combination of those two. In this case, it's and, so it would mean that it would only give you a true if the departure time is larger than 600, but also and as smaller than 2000. Yeah, so that's another way to then combine multiple comparisons with a Boolean operator. Okay, and now comes the interesting part. It's like how are missing values treated. And so NA basically means we don't know what it is, right? So it's missing. So we cannot say anything about it. And the interesting thing about in the chapter was like, let's say you have the age of two people, John and Mary, and you say John age is NA and Mary age is NA, and you want to compare them to each other, so you would do John compared to Mary, then you would get returned an NA because you don't know if they have the same age or not. You cannot make any statement about it, so it returns an NA because you actually don't know. The NA just, it doesn't mean it's not like not or anything. It just means you don't know. So and that's why NAs usually propagate through things, and that's also important to consider. And so here's something that's might be unexpected. You have X, which is some vector, and you want to compare it to an NA. It will just return an A for all your elements, not just the ones that are missing. And so to actually find the elements in your vector that are missing, you use a function called isNA. And that returns true for missing values and false for everything else. And so this here doesn't function work. That's just one of the examples. You use a vector and compare it to an A, so that's not useful. So you can use is an A and then just check which one of your values is an A. And then you see here the first one is true, you get a false, so it's not an A. The second one is an A, you get true, and so on. So that's pretty straightforward. And here's the other example, what it just said. So it returns an A true for anything else. So in this case, you have a numeric vector, and you have a 1 and a 3, and both of those give you a false. Only the NA give you a true. And does this come? Yeah, no, it doesn't come here. Okay, cool. So then then it's about how are NAs treated in Boolean operations. And so in comparison, NA will always return you an NA because it just doesn't know. But in Boolean, it really depends what your operator is. So for example, if you have true and an A, it will return you an NA because if an A would be a true, it would be a true. If it's a false, it would be a false. So it can't tell you. It just says it's an NA. But if you have false and NA, then it's definitely going to be false because no matter what the true value of NA is, and I mean with true the actual value of this missing value, it doesn't matter. It will always return you false. And so the reverse is true for the OR operator. So if there is a true in there, then it doesn't matter what value the NA is. It will always return you a true. While with a false, it cannot tell you, because if the actual value of the missing value is true, then it would be true. So it just returns you an NA. It can just propagates in that case. So that's often like unexpected, and you have to be careful. It trips me off up often, because it's just like the other thing where you compare, where you forget that you should use the is an A function, you use the equal operator, and suddenly like, why is everything an A? It's it can trip you off quite easily. Okay. And then here we do the examples for those missing values that we just went through. Okay, and then the special thing that I did not know, and that actually is not that atypical, I have to say, is that sometimes you want to know if your value is something a certain value, or if it's an NA, and then you can actually do that with an in operation. So in this case, that works. So it will return true for any NAs, but it also will return trues for any other values you're checking against for the equal operation. So I thought that was pretty neat, because I did not know that you can just shove it in there. Yeah. Cool. Okay, and now we get going to the conditional transformations. So one thing you can use logic vectors for is that you generate a condition, which is basically returns your logical vector. And then you, with the if else function, can say, okay, if this condition is true, return this value. And if this condition is not true, return the other value. And then you can also define if anything is missing. So if you have any NAs for that, what do you want to have returned? If you have null in there, it just returns you the NA, but you can also replace it with other strings or whatever other values you would apply in your situation. And then it says if there's multiple conditions you would like to check. So if you actually would like to nest if else's in each other. So if either the true or false, and you would be tempted to put another if else function in there, then that's usually a good case to just do a case when. And the important thing, it's hierarchical. So you're gonna write a lot of conditions, and it will go through for each of your values, it will go through the conditions, and whichever one is met first is solved first. So you have to be very careful with case when, where the sequence of the conditions that you're checking. Okay. And here's just an example that we check X if it's larger than 0, and then it's either positive. It gives us this condition. If it's true, it returns positive, so plus and VE, and if it's negative, minus VE. And then we see here, so the first three values would be -3, and would be -3, -2, and -1. So those are all negative, so it returns negative. For 0, it also returns negative, because X is still not larger than 0. So 0 returns negative, and then all the other ones, 1, 2, 3, returns positive. Okay, and here's the other example. So how can you deal with 0? So a case when first it checks the first condition, and then if that's true, it returns a 0. Then if it checks the second condition, if that's true, then it just doesn't continue. So that's important. So it would stop evaluating the other conditions. If this first condition is not true, then it checks the next condition, and so on. So in this case, again, as a reminder, the first three values are negative, the middle value is 0, and then positive. It returns minus VE for the first three, because it would always be not true in the first case. Then it goes to the next one, which is true, returns these, and so on. So that's how you can have this transformation where you have hierarchical conditions. Okay, and then the important thing, whatever you do here, these values that get returned, that are get returned, they all must be of the same type. So case when will give you an error if you have For example, here the 0 as a number, and then all the rest would be string. It would just error out because you mixed numeric with strings. So you have to be careful what you're doing. And so here it just lists the compatible types. So it's okay to combine numerical and logical, because any logical would be just be represented by 0 and 1s. Then strings and factors, it is the same, because factors can be just represented by strings. The only difference between a factor and string is there's only certain levels you can have with a factor. And then NA is compatible with anything. And I think that became more relaxed more recently, because I think it was actually complaining about that, because there's apparently different NAs. So numerical NA is not the same as a string NA, I think. And just recently, I think they changed that it's more permissive, that it understands, just picks the NA you need.
Yeah. So before we move on to like summarizing and subsetting, if you wouldn't mind going back to the last example with case one, because case one, like you did mention, there has been some changes that have happened as of recent. I think that dot default is like a new addition to case one, which I need to get used to using, because I used to do like at the end of a conditional statement, like to catch like everything else would be like you would use like true tilde whatever you want. But I think they added that dot default, and so I think you can do like dot default equals as dot numeric, as dot character. So like it will, anything else that don't add true into your like logic that you have in your case one, it will just default to the data type that you want, which
Yeah.
I think that's the change. I saw it like posit this year, and I was like, is that like, so I think that's what the new dot default does. I don't know if you know of that, Stefan, or if DJ, if you've come across anything, but that's like what I used to do, is like true tilde as dot whatever, but you don't have to do that anymore, I think is what they were saying.
Yeah. It's basically more explicit to say, oh, if nothing else returns something, then the default, it returns the default. It makes it a little bit more explicit, because the true equals whatever, tilde whatever, was maybe not as intuitive, I think, to be like, oh, that's how I catch all the other cases. So yeah. I think I started using case when that was still the case, but I had totally forgotten, and now usually dot default.
Yeah, and that was just like the one change, and then the conditional type, like having the same types obviously is a good thing as well. But then like when you also mention like there are different NAs, like that is also trippy too. Once you learn that, like R doesn't just have one NA value, it has NA numeric, NA character. So I think it has an NA for all the different data types, which once you learn that, you're just like, okay, this goes a little bit deeper. Like there's different types of NA values, and they're not just treated as like NA. So, but more of a comment than a question.
Yeah. And I don't know why that is. I was like, why is there different NAs? I do not understand what the underlying structures are. And I had thankfully never encountered a problem. So I just knew that was a thing that just changed it. And it makes it so much easier that now you just can write NA instead of being, yeah.
Because you have NA, you have NaN, and then you have NA real, NA integer, NA complex, and NA character. So, but
Oh,
like I
wow.
said,
Yeah.
I have no idea why those are the case. It's probably just a remnant of like something in S or like a previous language that preceded R. But it's just, yeah, if you really
Yeah.
want to go down that rabbit hole, you sure can, because R has many different NA types, which is just, it's just interesting. So, but yeah.
Yeah, and I think one of the reasons why they made it more permissive, it was like really hard to understand, because I think that the main issue was if your new vector was a different type, that caused problems, I think. If it was the same type, if it was string before and a string afterwards, you could just write an A. But if it was, I think, numeric before and string afterwards, then it would, if you just wrote an A, then it would kind of suddenly complain, because it would use a numeric NA instead of a string NA, and would be like upset. I think that was yeah. Anyway, but this is like really detailed. Anyway, okay, good. Okay, and then we already discussed this. Okay, and now we get to subsetting, and subsetting is something that's base R, and I think what is the chapter 27 or something where we talk about that. I actually really am bad at base R. I have used it so little. When I learned about the tidyverse, I was like, oh, this is so much easier. And so here's the explanation. So you basically use a logical vector in brackets to subset data, and subset is brackets. And so here, for example, you can determine your conditions. So you get any arrival delay that's larger than 0. And then you use that logic. So this generates a logical vector. And then you use here the flights, the arrival delay vector, and subset by that condition. And so that is a little bit less verbose because you generate here your other variables. So that makes it a little bit easier to understand. But if you combine those two things, this becomes very verbose. Just imagine your condition you're checking is a combination of, you do Boolean operations on this too. Like take any filter operation in dplyr where you have more than 2 conditions, and try to write that as a base R would make it very confusing, usually hard to understand in my experience. But for that, logical vectors are very helpful, and sometimes it's actually more succinct and easier to use the base R subsetting. So it definitely has many applications that makes it often easier to understand your code. But in many other situations, in typical data science applications, in my experience, it's often too verbose. Okay, and now how can we summarize a logical vector? And so there's a bunch of different vectors we can, functions we can use. So any and all returns a logical vector, and sum and mean will return a numeric, and we talk about what that is doing. And then you can also summarize a subset of your data. And so one important thing, especially about these functions up here, if there's any NA values present, it will return an NA, but you will often have situations where you just don't care about the NAs and want them to be filtered. And so often these functions have the NA remove option, and then you can just remove them with true. So you don't have to do like an extra step where you first filter all your NAs before you can do your summary function. That's makes it much more easier. Okay, and so the way that all works is basically it takes the logical vector and returns a single logical value. And so if all values are true, then it returns a true. If a single one of them is false, it returns a false. And any is when a single one is true, then it returns true. And if all are false, then it returns false. And there's just an example here. So that's very neat. That can often help you to just quickly see if there's any exceptions. So when you want to check if everything is true for this data you're looking at, then that would any and all would help you making sure that you caught everything. And then the neat thing that I think I learned only like 2 or 3 years after I learned programming is how you can use the mean and sum function actually on logical vectors, because the mean basically divide, let's do the sum because it's actually easier. So the sum function basically adds all zeros and ones together. And so that's a very quick way to know how many true and false values you have. So if you know the length of your data frame, for example, or your vector, whatever it is, and then you do the sum of it, of the logical vector, then you know how many of your values are true. That might give you a good, indicator, like, is this like a random occurrence? Does this often happen or not, whatever condition you're checking, or is this something that's really prevalent in your data and you need to think a little bit more carefully about? And then the mean is the same thing, that basically gives you a summary, like the proportion of the true values you have, because basically it does the sum and then divides it by the length of your vector. And so that's really neat to get an idea. So here in this example, for example, it tells you which proportions of flights are delayed on a given day. So here, just as a reminder, the dot by is basically the group by, just for this operation here, the summarize function. It groups this data by the day, and then you can just easily see what proportion is delayed. And the same thing is there, the count. So how many of the flights had a long delay. So that's a really neat way of summarizing the data. And then summarizing logical values. Now I don't remember what is happening here. Mean of all the arrival delays where it's larger than 0. Okay, yes. So here you basically use the condition to already subset your data. So you could do the same thing by do a filter operation before that, but sometimes you don't want that because you might do other summary functions where you want this data still in your data set. And so here, because of that, it subsets the arrival delay data to anything that's larger than 0 and gives you the mean. So just so you get an idea, what the mean arrival delay is. So that's pretty powerful. Sorry, that took me a little bit to understand what the data does. Okay, and I think that's it. Yeah, that's all of it.
Yeah, that's awesome.
And yeah, for me, the most surprising, just to summarize, was the in operator that you can put NAs for the comparison. I think that's very neat because that is, like I said, I faintly remember that I had this issue where you do the case when or as nested if else to kind of catch these kind of cases. So that seems very neat that you're able to do that. And pointing out that exclusive OR is actually how we use OR in the language. That can be very helpful in the beginning when you start out, because the OR, I think, doesn't make as much sense. When you're just starting with Boolean logic. Yeah, that's very neat.
Yeah, I think for me, outside of just understanding like, what are some of the gotchas with the Boolean logic and like NAs, just the summarizing stuff of just how succinct you can like get your code to get answers to specific questions by just using the foundation of understanding how logical vectors work. I think that's just super powerful takeaway from this chapter.
Yeah.
I don't know if anybody. Oh, go ahead. Go ahead.
No, I totally agree. It's so powerful. And then also the case when function is also powerful when you're like, I remember reading code from other people and it was like, this if else is so complicated to understand what's happening when you have nested if else. And it's good, like good practice to learn here. And then you can transfer it in general programming too. Like it's really, it has a good synergy it's a good habit to have.
Absolutely. I did some more digging about the TNF stuff. I don't know how far down the rabbit hole we want to go with that, but so TNF, okay, so to start out, true and false are reserved words, so you can't overwrite them.
Oh, okay.
TNF are defined in the base R package, because base is technically a package in R. So those are synonyms to TNF. So technically, you can overwrite TNF in your code. And so people suggest not using TNF because you can inadvertently overwrite it in your code. True and false, because they're reserved, you can't. You will get an error if you try and do it.
Oh, interesting. Okay, cool. Thank you for looking that up. That's really good to know. Yeah.
Yeah, because here's the example that I had. I don't know, like I said, I don't know how far y'all want to go down the rabbit hole, but like I'll share the R bloggers thing that I just popped up and looked at because I was curious too. Let me see if I can share my screen here real quick, just to show y'all what I pulled up here. So share. desktop one. So here's the example that I came up, and actually you can look up the reserved word. So if you go like question mark, if you go question mark T, question mark F, it will bring up the logical, like the base R logical vectors,
Mm.
like explanation. And so you have the reserved words true and false, but then you have the synonyms T and F. But then if you try and play around with it, so like here, I just tried to change true to a character true, and it's like, nope, you can't do that. But then if you do it
Mm-hmm,
with a synonym T, you can absolutely do that.
mm-hmm.
So be aware, I guess, is the one thing that came up with it. But yeah, it's interesting to know like that true and false are technically reserved words. Like that is part of the language. It's not like a base R package thing. It is like a complete reserved word. So the
This
more you
is
know.
fascinating because it would be such a bad thing to just have a single letter variable that means something else than true or false. That's T. Like, how is that? I mean, I see that, of course, like time, you could totally see, well, although that would be a lowercase t. But anyway, it seems like bad habit. But it would totally trip you up if you get someone else's code and they redefine that. Yeah.
Yeah, I'm sure there's more in here that you can read. And I don't know why that's the case, why in the base R package they decided to create these synonyms, but yeah, it's interesting. I mean, the other thing too that's really interesting is like zeros and ones. You can have double zeros and double ones, but you can also have integer zeros and ones. And so it's just there's just all these little like quirks about like the data types that you have. I mean, pick how far you want to go down the rabbit hole to learn more. So anybody that's a beginner watching this later and you're like, what are they talking about? You don't have to necessarily worry about it, but like some of these things will pop up as you learn that,
Yeah.
it's interesting to kind of dig into. So I
And it
don't know.
might be nice
Any
to just hear it, right? Once you heard it, you're like, oh, I have a faint memory that there's something different about T and F, and I should look into that. Yeah.
yeah, the whole like multiple NAs thing just what the day that I learned that it was just like why do I need to know this? But it's it's like you said, you hear it one time and then you like learn about it and they're like, oh, okay, I can dig into this more and understand it a little bit more about like why R made this design or the people who designed the language, why did they make this decision? So, but cool. DJ, do you have anything to add or do you have any other comments or questions or
No, I don't have any questions.
cool,
Okay.
cool. All right, cool. Well, I can I mean, Stefan, do you have anything else you want to add or any other things that you think are interesting or?
No, no, that's it.
All right, cool. Well, I really appreciate
Awesome.
everybody joining in. Obviously we'll take next week off and then let me do stop here.